Thank you, everyone. As mentioned, I'm Lauren Margulieux. I'm an associate professor at Georgia State University in Atlanta, in Georgia, in the United States. Or because we're in Lausanne, you might know it as the site of the 1996 Olympics. And I would also like to thank the organizers for having this lovely display to hide behind. But I am also 7 months pregnant, which in this context means that I run out of breath very capably just by speaking. So I might have to stop and take a couple breaths at various points, which is no different than when I'm climbing the hills outside. So today I'm going to talk about computing across the curriculum, or CS knowledge and skills that everyone values. And the reason that I'm talking about this today is because I am, in my university and for a lot of the United States, one of very few computer science education researchers who's in a college of education. Most of us are in computer science departments, and so we don't really have access to teachers. However, given my unique position, I have shifted my research almost entirely to integrating computing into our teacher preparation programs and studying how computing can be useful for everyone, especially those who are not computer scientists. So I'm going to talk today about integrated computing. And integrated computing is the use of computing tools in non-CS learning and problem solving. So in your math class, in your science class, in the United States, it would be your English class. And how can computing be useful for both teaching those subjects as well as preparing students with a general computational literacy? So integrated computing into other disciplines is valuable for the same reason that we find computing is valuable in non-CS professions and in personal life. And that's because it provides a computational thinking and a logical way of thinking about problems. So it gives you a problem-solving procedure to follow. And it also automates problem-solving processes. So this is where I usually hook our teachers, is that I say, what is your least favorite thing to do? You can automate that. And then they get really excited about learning computer science, something that they have never been excited about learning before. Some of the additional benefits in education is that it teaches technical skills. So at least in the United States, we have a big problem of people sort of being intimidated by computer science. They don't necessarily know what it is, and so they don't necessarily want to try it out because they've heard that it's really hard and it will completely tank their grades and make them look like they're stupid or make them feel like they're stupid. And so integrated computing allows them a space to explore these technical skills in sort of a safe space, and a space where they already understand a little bit of what's going on because it's in their math, science, or language arts classes. I also really like to use it as a metacognitive tool, which is what I'll talk about next. So teaching the computer to improve learning is the best way I've found to sell integrated computing to teachers, because the teachers already agree that teaching is an effective strategy for improving learning. And so we teach programming as just teaching the computer how to do something. So if teaching is a good way to learn, programming is just teaching a computer. Computer is a very particular sort of learner. It never gets tired, doesn't bring misconceptions, doesn't misinterpret what you say. All of these things can be used as a metacognitive tool for learning. And this benefits the individual, both because it identifies misconceptions that you might have or missing knowledge through finding bugs in your program and debugging those bugs. I found, especially with elementary primary teachers, that rubber duck debugging is very popular. They're like, you mean I can get a set of like 30 rubber ducks for my class and that is relevant? And I'm like, yes, and they get very excited. Also, socially, by writing a program, you are formalizing your knowledge into an external space, and that allows your teacher or your peers to look over your shoulder and recognize what your thought process is already. So that's sort of the framework that we use when we integrate computing at Georgia State University. Now I'm going to walk you through sort of some of our specific implementations that we've been doing. So our approach to integrated computing, this applies when we teach across all different disciplines and all different grade bands. So I work with all teachers in our college, and we teach computational thinking with programming. We don't teach it sort of as a separate thing. We just teach. I found that when we tried to teach computational thinking without programming, I understood how it applied to computer science, but the teachers didn't really understand how it applied to computer science. And it's because they don't really have any experience with programming, so it's really hard to explain this process of programming without getting them some experience with it. This was particularly salient when I asked them to write pseudocode one time before I had showed them any sort of programming, and they were like, I don't know what you mean. And I'm like, it's like you write instructions, and they're like, okay, then like do this thing. I'm like, no, you have to break it down. And then I showed them programming, they're like, oh, I get it. It makes sense. So we do teach computational thinking by teaching them programming, usually a block-based programming, because we don't have a lot of time with them. Usually I get about 2 hours with them to teach them an activity that they can do in their class. We also connect computer science to prior knowledge. And this resonates well with our teachers, is that computer science is sort of the new kid on the block, if you will. It's a no domain. It's built on things from science, from language, and from math. So if you already know about those things, which you do, then you already know a lot about computer science. We just have to figure out what those connections are. And so there is also misconceptions that can come from this prior knowledge. So when we start talking about variables in computer science, that means something very different in computer science than what it means in math and what it means in science. So it's important to point out those potential misconceptions. Our definition of computational thinking, because if you ask 10 people what their definition of computational thinking is, you'll get 15 different answers. So our definition of computational thinking is asking 3 questions. Should I get a computer to help me use this? How do I get a computer to help me? Which is where we spend sort of most of our time. And did the computer do a good job? And so those first and second questions are really important to our teachers because that helps them with understanding how it applies outside of computer science. We teach 5 concepts: abstraction, which is sort of related to pattern recognition, algorithms, automation, decomposition, and debugging. And so we teach abstraction, algorithms, and decomposition as something that you already do in pretty much all the problem solving that you do. However, the automation and the debugging is sort of the computer science specific technical skills that we're going to teach you. We use a co-design model for our integrated activities. So we we treat integrating computing as solving a shared problem with the teacher education faculty. And this is how I actually got in the door with a lot of our teacher education faculty, is I said, what is a problem that you are trying to solve in your class? And this sort of coincided with a year where we had to update all the technology across all of our programs. So it was really convenient for me to come in and say, tell me how I can help you. Like, you need to up your technology, I can do that for you, just tell me how I can help. And so some of the shared problems that we solve, basically I see it as creating a computing solution for a problem that they're having. And that makes it much more sustainable rather than saying, here's another thing for you to do in your course, which they get constantly. So some of the things that we found have shared problems is a pedagogical problem. Maybe they have an activity that is their least favorite. They hate teaching it every year. It's least interactive. All they know how to do is to stand and talk in front of people for teaching this thing, or that their students conceptually struggle with it. And maybe a visualization through computing can help them understand that concept. Another way that we solve problems is through activity types. So this is more related to computing. So if you have an activity that involves a lot of repetitions, like data collection in science, let me tell you how to automate that. Also tinkering. So if you're just exploring a new concept, you can sort of tinker with the values and come up with more of an intuitive understanding just by playing and tinkering with the concept. And then visualization is another big one that a lot of our teachers find helpful because they are trying to teach something that you can't necessarily see, but the computer can help you visualize it, especially for your students. And then we also solve some problems based on the computational thinking approach. So pattern matching, especially in elementary or primary math, is something that a lot of our teachers are interested in. decomposition, solving big problems by breaking them down, or automating processes that they find tedious and don't like doing. So I'm going to share with you an example from our middle school, which is a lower secondary science classroom. And there is an activity guide if you want to follow that QR code or that link. And so we, in this activity, are creating a visualization of an electromagnetic wave. And the way that we go about this process is that we create the very most basic bare bones program that we can. And then the process that we go through is we make the program smarter and smarter and smarter. And so this is that process of teaching the computer how to do something. So at the very start, we just create a single wave. And you can see this is a logo-based programming language called pencil code. And so you pull out a pen, make it whatever color you want, and crank up the speed a little bit so that you can tinker and iterate. And then you go forward, you turn right, you go forward, you turn right, you go forward, turn left, you go forward, turn left, and then you're done once you go up again. So that's the very basic bones program that you start with. Now let's make it a little bit smarter, because you don't ever see just one wave. When you're talking about waves, you see multiple. So now, instead of do that process all over again, we're going to add a loop. And we're going to stick that code inside the loop and repeat it as many times as we want. And so you can play around with that to change how many times it repeats. Now let's make it a little bit smarter. So each time in the previous one, we had it moving forward a static amount of a static distance. So if you wanted to change how tall the wave was or how wide the wave was, you would have to go and manually change that every single time. However, we can add variables and talk about the wavelength and the amplitude of the wave and set those values at the start. And then instead of saying move forward 100, say move forward the amplitude of the wavelength. And this reinforces those science principles, because now you have to understand that a wavelength is one length above or below the resting line, or an amplitude is one length above or below, and that a wavelength is the entire span of the wave. So in order to match up the values, you have to understand that you're going up one amplitude, but then you're only going over half of a wavelength. And that helps you discuss that science. All right, and then moving on to the next one to make it smarter, now we're going to change the for loop that repeats for however many times you want to a while loop, because at the very bottom here, we're going to change the wavelength each time it goes through to make it shorter and shorter and shorter. And this is usually a great place to intentionally introduce a bug, because you add this in a for loop and you repeat it a certain number of times, and eventually the wavelength turns negative and it starts going backwards. So we add that so that the wavelength is updating each loop, and we add it, make it a while loop so that it only works while the wavelength is positive. And then the last step is that we add a bunch of conditionals. Probably not how you would solve this in computer science, but for our purposes in science education, it works just great. But we add a bunch of conditionals that change what the color of the wave is based on what the wavelength is. So if the wavelength is greater than 40, then it's red. If it's less than 40 but more than 35, it's orange. If it's less than 35 but more than 30, it's yellow, so on and so forth. And you talk about how that sequence is important and how you could invert that sequence if you made it greater than instead of less than. I think that might work. I don't know. I didn't thought through that. But and so now we've introduced loops, variables, and conditionals to students to help them understand how electromagnetic waves work. And they've gone through this process of automating, creating this visualization. And they tinker with it along the way. You know, you can test out, if you change the wavelength by this, what do you expect that it would look like? And that helps the students think through that process of what is a wavelength how does it play into this visualization? All right, our second example is from not middle school science. This is high school language arts. And so we created a chatbot. In the previous example, we build that program from scratch. So we start with that very basic wave and we make it smarter and smarter and smarter. In this example, we use the opposite approach, which is we give them a fully formed program, and then we use the use, modify, and create, or it's sort of more heavily modify than create. But we help them understand how to use the program, and then how to modify it, and then how to modify it even more to serve their own purposes. So in this example, you are talking to Lady Macbeth. Lady Macbeth by Shakespeare is taught. That was all of these examples. They were topics given to me that I was like, I don't want to teach it the way that I teach this anymore. So come up with something. So in this chatbot, it's Lady Macbeth, and you can chat with her, and she recognizes keywords. Of course, this is a little bit outdated because students' understanding of what a chatbot is a little bit different in the past year. And it's still a way to sort of introduce those computing concepts, though. So we have them use it. We ask them to try out different things that will introduce errors. So we ask them to misspell words. What happens if you have multiple keywords? How does that affect the output? And then what happens if you add punctuation, if you capitalize a word, all these sorts of things that if you could see the bottom of the program here, you would see that it's sort of cleaned out of the data. It converts it all into lowercase, removes any punctuation, that sort of thing. And then we ask them, once they're comfortable using it, to modify it. So in this first block, when it says hello, hi, and it returns hello, I'm waiting, we ask them to add an additional greeting, such as hey, to that block. And this actually requires them, one of the things I love about pencil code, this programming language, is that it's a hybrid language. And so it is block-based, but you can also make it text-based, because we found that students very quickly sort of get frustrated with a block-based environment. They find it very tedious after about 30 minutes or so. And so being able to switch over to that text-based environment is very helpful for helping them. They feel like it's more authentic because they're typing instead of using block space, but it's also just less tedious. So we switch over to the text-based environment and we have them add hey in there. And then we also have them add an entirely new block. So we have them copy a block, paste it, and then completely change what the keywords are and what the response is. We also have them heavily modify. So we can change it from Lady Macbeth to any other literary character that they're studying, or we can change it from this chatbot to creating sort of a dictionary that, based on whatever they're reading, they can add examples of literary devices. So you can have it ask what is alliteration, and it'll give you a definition of alliteration and then examples from the book that they're reading. Some other examples are sound and light refraction. So this would be in upper secondary science, and that's building upon that wavelength, that wave that I showed you. And so this adds what happens to a wave as it enters through different media or as it reflects in different media. So we have a sound one that shows how the wavelength changes when it enters a different media and how it changes based on different refractory indexes. We also have a drawing with geometry. This one is my favorite one because I can use it with any grade. Like, it's relevant to primary students and it's still sort of relevant for upper secondary students. And it's also a really low barrier to entry because you're basically just you're drawing with geometry. So you're using the loops to draw a lot of iterations of things, and it creates these really cool patterns that you wouldn't be able to draw personally. And then in primary math, like I mentioned, pattern recognition, so pattern creation and recognition is a big learning objective in primary math. And so we have students create their own patterns and then give it to their peers to see if they can figure out what the pattern is and if they can recreate it. We have also word problem decomposition, which we use at all grades in math. So sort of figuring out what are those relevant bits of the word problem and putting those into variables or whatever it is to solve word problems. We also have a corn growth simulator. And so in the United States, we have dual language programs. You probably have that here. But students who speak Spanish will learn science in Spanish. And so this was an activity that I was asked to create to sort of connect to a wider curriculum about like corn that they were learning. And so we put in like hardiness measures and what the rainfall was and what the drought resistance was, and you could stimulate the growth. We've also in kindergarten, this is towards AI. I'll talk about AI a little bit towards the end of this section, but we talked about how AI learns to categorize different things and how that's similar to how students are learning to categorize things in pre-kindergarten and kindergarten. And then a fitness calculator for our students in physical education and how they can automate calculating fitness scores. And so what's important to draw out of these types of activities is sort of what they allow teachers to do that they wouldn't be allowed without the computing tool. So in the sound and light refraction, it's helping students visualize these electromagnetic waves that are obviously too small for us to see with the naked eye. Drawing with geometry, it allows them to tinker with different geometric principles and sort of explore how angles and all those sorts of things work. Pattern recognition and pattern creation and recognition is also a visualization, especially for those younger students. Having that visualization is really helpful. And then the rest of these are just how to automate that problem-solving process. So how do you solve a word problem of a certain type? Or how do you simulate things of a certain type? Or identify categories or calculate someone's fitness? And this is all automation, which is something that computers are uniquely let you do. Some lessons learned. So when I started this work, I had these lofty ideas that we were going to teach teachers how to program, even though they had never programmed before. And apparently we were going to do this in like 2 hours. And then by giving them this one example and walking them through this one example, they would be able to create their own activities based on whatever it is that they were teaching. That didn't work. Not even for the activity that we gave them. Like when we went to student teaching and they were practicing in the class, they're like, can't you give me your program to like make sure that I'm doing right? I'm like, absolutely. So we have decided to not try to let students or the teachers not try to prepare them to create their own activities, but instead to design pre-designed activities for them. Because if you give them an existing program and a lesson plan that they've created for that existing program, then they're really comfortable really quickly with those activities and they can actually use them in their classroom. So it decreases the time to adoption by giving them a pre-designed activity. It's actually pretty quick to create these pre-designed activities. It takes me probably about 30 minutes. And we've looked at teaming up with computer science teachers to help pair up an idea for an activity with the actual program to create it. And it gives students or the teachers an unparalleled level of confidence compared to if they had to use their own programs. So we've really leaned into this pre-designed activities. Some resonating practices, I've already mentioned some of these, but teaching the computer as a way of learning is something that immediately resonates with the teachers. Another thing is that when they do student teaching, when they take these activities into classrooms with students, they find that the students get really engaged really easily because it's very interactive. And so that's a really positive experience for teachers, even the ones who are very hesitant and very uncomfortable with it. After they do the student teaching and they see how engaged the students are, they get very much more on board with using integrated computing activities. And then we also have tools to build, or using integrated computing as tools to build metacognition and to debug that sort of thought process, that problem-solving process is something that resonates with them. They also really appreciate when we talk about relationships to prior knowledge. So how computer science relates to science or math or language arts or whatever discipline they're teaching. So the second year effect in applications to other concepts, this is where I'm going to talk about AI a little bit. One of the reasons that we have decided that it's completely fine for teachers to adopt pre-designed activities rather than create their own is because we found that the second year that they go into integrated computing, they start to have all of these ideas about how they could use computing in the classroom. When I'm first talking to them in those first 2 hours, they don't know what computer science is. They only know programming as something that's scary. Like just getting them to the point of doing one activity is, enough for me to ask of them. However, once they do know what computer science is, once they do have some experience with programming, they find that it's everywhere in their lives. And they start to think of all these other activities that they could do using integrated computing. And so that's where we get a lot of the buy-in is actually in the second year of working with them. And they come up with all these ideas for how they could do other integrated computing activities, which is where we come in and say, yep, we can help you with that program. Because they don't have the knowledge yet to create the programs themselves, but they can see how it applies to their lives. And related to AI, because you can't give a keynote without talking about AI at least a little bit, is this year they are all bought in on AI. Like, I'm no longer having to go to people. They are coming to me and saying, what is happening with AI? How can I use it? The surprising thing to me, though, is that the faculty that I work with, they're more interested in how to use AI in their own classroom. Like, how do I use it to help me grade things? And they're not necessarily interested in how the teachers are going to use it with students. So that's something that we keep sort of having to return to is you can use it for this and then teach your teachers how to use it for that. But that's all of the projects basically that I'm working on this year is how to use AI in computer science or in integrated computing. All right, so now that you know what we do at Georgia State in terms of integrated computing, I want to talk more broadly about integrated computing activities used beyond Georgia State and for different purposes. So we've done 2 analyses of integrated activities, so publicly available integrated activities. One we talk about as sort of a bottom-up analysis because the criteria that we used for including the curricula in the analysis was that it had to include non-CS learning objectives. And so these were activities that are not necessarily trying to teach computer science. They're using computer science, but their main learning objectives are in the discipline that's integrated, so science, math, etc. The other one that I'll talk about after is the opposite. So it is integrated computing activities that are primarily trying to teach computer science, and what do those look like? So our goal of this analysis of integrated computing activities is to better understand computational literacy across the curriculum by examining how computing is used and useful outside of CS. So this is why we focused on that bottom-up approach of if the learning objective in non-CS disciplines is the center of the activity, what do people find useful? Like what elements of computer science are they adding? We found that a lot of prior work focuses more on a top-down approach, sort of previewing topics that are taught in intro programming, at least sort of that's how they're designed. And so that's why we chose this bottom-up approach, is what computing concepts are used when the discipline learning objective is primary. Luckily, there's too much to analyze if you leave it completely open-ended, so we had to narrow down our scope a little bit. So we had the non-computer science learning objectives they had to include. This means that the benefit is that you're getting something primarily that teachers have made. So that teachers who either are computer science teachers and they teach something else, or they, for some other reason, know programming, they've created these activities for their class. However, the limitation is that they're not necessarily trying to teach computer science. So, that's not a big part of what the activities are in a lot of cases. We also had to limit it to blocks-based languages, and this is purely just so that we could actually complete the work. However, we chose blocks-based languages because that is what teachers are usually reaching for when they are first trying to integrate computing. However, it has limitations in that there's lots of excellent text-based language integrated computing activities as well. And we'll talk about some of those in the next analysis. We also required the activities to be free resources, so something that anyone could go to the internet and download. And we didn't allow them to use robotics or physical computing just because of the cost of those activities. So there's not a database for these activities. It's not like you can go to the Association for Computing Machinery and say, give me all of the activities that integrate computing. So what we did is not a systematic review because there's no way that we could systematically say we got everything. What we did go to was repositories, especially in different languages, and curriculum that had been developed and had been published in the academic literature. And then we also did a Google search using a combination of terms like computational thinking and integrated and CS plus science, CS plus math. That didn't really yield a lot of results that matched our criteria, but we tried it anyway. What we ended up with was a database of 84 curricula or activities, and a lot of them were in math, language, or science. Some were in art or music, history, or others, like foreign language. And the age range for the activities, so that sort of lower primary, we had 10, upper primary, we had 46, so this was a lot of the integrated computing activities. And then once you start to get into secondary, you have 14, 3, and then there were 8 that said it could be used for any grade. There was a lot that used the language Scratch, several that used pencil code, some that used AppLab, which is code.org's programming language, Starlogo Nova for science activities in particular, and Scratch Junior, which is sort of the pre-reading version of Scratch. And then they also had a difference in minimum amount of time to complete the activity. Most of them would take less than an hour, which sort of makes sense if they were mostly in primary school. But some of them took 1 to 3 hours, some 3 to 8 hours, and very few took more than 8 hours to complete. So what did we actually analyze these activities for? We scored them for the programming concepts that we taught. So we wanted to know what are the CS concepts that are taught when you're integrating computing. So we had a few different categories: variables and data, which included variable, lit, and list; operators, algorithmic, relational, or Boolean; loops, for loops or while loops; conditionals, if then or if else; function, defining and calling a function, or using the parameters of a function. And then we had some not programming concepts, but they were, so prominently used in these block-based environments, especially in Scratch, that we needed to include them. So movement, moving a sprite around. Cartesian plane, so you use the Cartesian plane to locate different sprites or objects. Angles, turning or rotating at a different angle. And then back to computing concepts, we had components, so a multimedia object such as a pen, a sprite, any sort of object like that, and the properties of that object. And then an output, so a string output, an output that calls a variable. And then we actually had a separate category for string and variable, just because that's a slightly different procedure. And also inputs. This one was hard to quantify because as the programmer, you're like creating all the inputs, but we treated inputs from a user as separate from inputs from the programmer. So if a user was having an event, triggering an event, writing a string, or writing some sort of numerical value that they would enter. And so this is too small to see, but I'm going to go into sort of each of these categories. But I wanted to show you, out of these 84 curricula, there was a wide range of how often these concepts were used. So basically we had a yes-no analysis of yes, this activity included this concept, or no, it didn't. So the most popular concept that people used were properties of multimedia components, multimedia objects being right below that properties. And then the least common, down at the bottom, was Boolean operators. We also have different colors for science, math, language arts, and other, so you can see what the distribution is like. All right, so the most frequent programming concepts that we saw, which were in greater than 50% of the activities, were properties of multimedia objects, the multimedia objects themselves. The reason that these are slightly different is because some of the activities already provided a multimedia object that the student then just changed the properties of. Events, a lot of times this was the press the green flag in Scratch to make the program go event. Movement, so moving an object around the screen. A for loop. And then a string output, having usually a character say something. Variables, and using the Cartesian plane to locate an object. So you can see a lot of these are not sort of what you would teach in an intro programming class. You wouldn't really be teaching multimedia objects or their properties, events. You might touch on movement, especially not, because you're not using this block-based paradigm. So the for loops, string outputs, and variables are really the concepts that you would be teaching in an intro computing class, but they're almost not a full day of instruction to teach these different concepts in intro programming. The next group of programming concepts is the 25 to 50%. So in 25 to 50% of the activities, we call these common. So using angles. And you can see that this is especially common in science or math, but not so much in language arts. I wonder why. You're probably not using angles in language arts that much. Calling or defining functions. Calling a variable as an output. Using an arithmetic operator, again, very common in science and math, and not so much in language arts. Using an if-then conditional, and relational operators. So this is where you're starting to get more into those concepts that you would discuss in an intro programming class, but they're in less than 50% of the activities that we analyzed. And then the uncommon programming concepts were used in less than 25% of the activities. And these are a user inputting a numerical value, having a string and calling a variable as an output, using parameters of a function, a while loop, if-else conditional, a list, inputting a string, or using a Boolean operator. So as we get farther down this list, sort of the more advanced computing concepts start coming up, which makes sense. So I'm not saying that these activities are wrong, because they're not teaching what I would teach in an intro programming class. That was not the point of this analysis. The point was to understand, what do teachers find useful when they're integrating computing into not a computer science class. And so we found that visualizing, a lot of the activities were trying to visualize something. So they were leaning on those multimedia properties, those multimedia objects, movement, and all those sorts of things. And they weren't really focused on automating information processing. So they were focused on animation rather than automation. 12% of the activities that we included had no concepts that I would consider information processing concepts. And again, I'm not saying that that's a bad thing. Those included some of the ones that I had created for our teachers in our programs. But I did want to be cautious moving forward that we're not equating integrated computing with just a different version of EdTech integration. Because a lot of times we are using the computer or using programming as a different way to complete the exact same activity that we had before, like drawing. In this example, we can draw an isosceles triangle in one of two ways. We can do it completely manually by saying we're going to turn right this degree, move forward, turn right this other degree, move forward, etc. Or we can go a step farther and automate that process. So we can figure out what is the formula for drawing an isosceles triangle based on the angle that you're given, create a variable for that angle, calculate the other angle based on that variable, and then draw out the program like that. So in the automated version, all you need is to change that first variable, and the rest of the process is automated for you. Whereas in the other version, you would still need to manually go through each time, each new problem, and figure out yourself how to solve that problem. And so that's what I mean by being careful to not confuse integrated computing with just a different version of EdTech integration, which is using programming just as another medium for doing something. So some recommendations for integration. Like I mentioned, I'm not trying to say that the activities that we found are bad in any way. I want to honor the applications that teachers find, because I'm not going to tell you that, what you're doing is not good enough, so you should do it better or stop. That's not a useful way to do it. However, I do want to sort of empower people to actually go into these automation activities. What we did find is that for loops and variables are very common, even in these sort of more animation-focused activities. So these are basic information processing tasks, but they are sort of an on-ramp to advanced automation. And like I mentioned in the first part of the talk, doing something to get you to understand what programming is and what computer science can do for you can open up the door for you to see it in other aspects of your life. I was really surprised that conditionals and operators weren't more common than they were. And I think this is just because the programs that were used are not that complex. Like, they're not making decisions, they're not calculating things or comparing things. So that's probably just a paradigm that would need to be different. And then I don't want to make enemies, but the use of functions in these activities I do think was problematic, because you would be defining a function and then calling it exactly once. And I tried to do that with the wave activity that I showed you earlier. I was like, we're going to make a function and call it wave, and then we're going to call it once. And people were like, but why? I was like, that's a good question, because functions are actually a relatively hard concept to understand. And so if you're not even using them in a way that's beneficial, it's really hard to understand what they're even for. So that's why I'm not saying functions are bad, but if you see an activity that defines a function and then calls it once, I would ask you to question whether that's useful. All right, so the other version of that analysis is looking at integrated computing activities from a top-down angle. So when the purpose is to teach computer science, what sort of activities do we find? And so the goal of this analysis was to better understand how computing concepts are taught in non-CS courses and the depth at which they're taught. So our scope was they had to include CS learning objectives. They had to include 5+ hours of instruction. So unlike the activities that we did last time, which were mostly less than 5 hours of instruction, these were more than, just because we wanted to look at the depth at which concepts were taught. Again, they had to use free curricula. However, we included those that used robotics this time. And to narrow down the scope, we looked at only primary and lower secondary. So in the US, we'd say K through 8, but sort of before you start, because we're looking at these classes as an on-ramp to an intro programming class, which is typically taught in that sort of upper secondary range. So we found 27 curricula that matched these criteria, and they included 519 lessons, or about 600 hours of instruction. And so the lesson is that level of analysis that we looked at. We didn't look at the curricula as a whole. We looked at, for each lesson, did it teach this concept? We also expanded our framework beyond programming to all of the concepts included in the K through 12 CS framework, just because these are used sort of as standards worldwide. And so those concepts that we included were for programming concepts, same as the prior analysis, but also non-programming concepts like systems or networks or the internet, and CS practices, such as collaborating around computing. For the results, the programming concepts had very similar results to the prior analysis, which was very surprising, at least to me. My colleagues say that they weren't surprised by these results, but I was, because I was like, the purpose is to teach computer science, and in the prior analysis, we found that it didn't teach much computer science, so I thought this would teach more computer science, but it didn't really. So the most common concepts were still those multimedia objects and properties, movement, events, outputs, for loops, and functions. The most uncommon concepts were inputs, conditionals, and operators. The only one that really switched categories was variables. So variables were less frequently used in this analysis than they were in the previous analysis, probably because variables are just so central in science and math that those were common elements taught when those learning objectives were centered, rather than when the computer science ones were centered. The depth of instruction, we looked at the type of engagement that students were doing. So they were either using a program, modifying a program, creating a program, or creating it in an unguided way. So instead of saying, you're gonna make a conditional and you're going to draw, pull this block out and do this thing, it's just make a program and it has to include X, Y, and Z. Create was the most common type of engagement. So they moved pretty quickly in the curricula past the use and modify stage and were just creating their own programs. But we did see 3 sort of patterns in the curricula. So there were the activities that had, or the curricula that had limited concepts, usually based on the programming paradigm. So they were using robotics or Scratch Junior that were very limited in the concepts that they even offer. And because they were so limited in scope of the concepts, they were pretty unguided. So it said, make the robot do something. And that was sort of the instruction that they got. The second pattern was recurrent use of a subset of concepts. So they would use the the multimedia objectives, the properties, movement, and events, and they would use those in all of their lessons. And occasionally they would add other concepts, like conditionals or like loops. And these were largely creating programs. And then the other set of curricula, the last pattern, was they used a wider range of concepts, but usually in a use or modify sense, not creating their own programs. The non-programming concepts results. So the concepts that we looked for were computing systems, networks and the internet, data and analysis, and impacts of computing. Most lessons did not teach these concepts, especially networks and the internet and data and analysis, unless they were like a data science curricula. And then they talked a lot about data and analysis. And then the curricula for older students, so students in those lower secondary grades, they included more of these non-programming computer science concepts, but it was still pretty rare. The practices, so the computer science practices, there's 7 of them, each with 3 to 4 sub-practices, so about 28 in total. The most common ones were including the unique perspective of others, cultivating working relationships, describing and justifying and documenting computational processes. So these top 3 were sort of the most common, and they're all about sort of these more social aspects of computing. And then the bottom ones were more about actually creating the program. So modifying an existing computational artifact, creating a computational artifact, identifying complex interdisciplinary real-world problems, or extracting common features. So in terms of programming concepts taught between these activities that centered computer science the computer science learning objectives, or ones that centered disciplinary learning objectives, they were similar in terms of the programming concepts taught in previous analysis. So they still had that emphasis on automation, on animation rather than automation. And I was surprised because I thought that if you had a curricula that had 20 lessons or so, that you would sort of be building one program and building on it throughout. But that wasn't really what we saw. We found that each lesson had its own different program that you're working on. And so maybe stringing together lessons in a more curricular way would allow you to get to more advanced concepts. Other concepts and practices, so other CS concepts and practices, were not taught that much. And this is important only because a lot of times in integrated computing, you're saying, well, the goal is not only to teach you programming, like that's just one aspect of computer science, but this would suggest that you're not learning other aspects of computer science as well. And again, I'm not saying that these activities are bad. This is probably really appropriate for a first introduction to computer science. Just, using a program at all, thinking programmatically or thinking algorithmically and putting things in sequence is probably really appropriate. However, I do want to be aware of what computer science teachers think students are coming in with in prior knowledge when students have engaged in these integrated computing lessons before. So just because you have students who have done integrated computing in their primary education does not mean that they're very familiar with variables or functions or loops or conditionals. And that's the end. I did want to put some resources up. So there's integratedcomputing.org has all of the activities that we included in our first analysis. And then to learn.
I just put up your name now.
And then if you want to learn more about our work at Georgia State, there's a paper about that. And the first analysis I talked about, the bottom-up analysis, is published. The second one where I talked about the top-down analysis is still in progress. So hopefully none of you were asked to review that.
Thank you very much, Lauren. A great talk. Let's take a few questions from the audience. We'll circulate the microphones.
Thank you for a really amazing talk. And I would like to ask a short question about debugging, because you mentioned debugging in among 5 computational thinking, and then there is almost nothing about debugging. Maybe it's too heavy, or it is, you can connect also with some like error, like according like Puppet wrote in Mindstorm. So what's your answer?
Yeah. And we don't, in the lesson plans, if you go to one of those links, there is a little bit of information about expect students to make this error and that sort of thing. But usually they make enough mistakes that we don't have to intentionally bring up debugging. It's sort of just part of the process. So we started this work in 2018. And last year when I was teaching, I was like, man, I've been doing this for too long because I'm not making enough mistakes. Like I'm not being able to demonstrate that debugging process. So I've started very intentionally adding points where we are making mistakes and saying, what do you think is going on here?
Hi, I'm Timon from Munich. Thank you for the great talk. I wanted to ask, like, in our context, the situation is a bit different because we have in most places a computing subject where a lot of the stuff is happening, but we're still discussing a lot about this like general teacher education. What computer science knowledge do they need? And like one take we have is their subjects are changing because the scientific discipline behind that is changing. We see that in the natural sciences, we see that also in the social sciences, that computing is the driver there for doing things, simulations, data analysis, and stuff like that. Is that also like, I saw in a few of those examples that exactly was the thing, like the core simulation thing. Is that one way to like have a even more integration than just use it to animate, but we use it the way we would use it in this particular science that they are teaching and that their main goal is about?
Yes, and we try to make the activities as authentic as possible in that way by saying, if you're in science, you would solve a problem like this, and we're going to use the computer to help you do that in that sort of automated information processing way. As with a lot of education, we fall short of that authentic connection a lot of times, especially because we're trying to teach the programming at the same time. So a lot of times we're just reinforcing concepts that they've already seen, like in the wave example, we're reinforcing those wave and amplitude concepts that they've already seen. But we're not necessarily, like, we're giving them an option to tinker with it and explore what happens when you change those values and sort of just develop an intuition for it, rather than saying, this is how a biologist would solve this problem.
Yes. Excuse me. Thank you for your talk. I have a question about your interdisciplinary approach. There are sometimes some fears that interdisciplinarity can induce confusion, either because it mixes two terms that can have the same name but are refer to different concepts, as you mentioned for the variables, or also because it adds complexity to master two different visions at the same time. Did you notice that effect, and what the benefits of the illustration worth it?
Yeah, and so variables is one of those terms that causes a lot of confusion. Decomposition is another one, because decomposition in literature is used sort of similarly to how we use it, but decomposition in science is a completely different thing. And so in terms of addressing those, that's why we have sort of the two different approaches of we're going to build the program from the bottom up and make it smarter and smarter and smarter, or we're going to give you a complete program that you can tinker with, use, modify, and then create. And that's just a call based on, or sort of a judgment call based on what the faculty member is asking me to do versus what's sort of reasonable to do. So that's something that we're always thinking about, is trying not to add too much in terms of the extra work that we're asking people to do. And it just depends where the student is in that learning process for which of those approaches we use.
Okay, thank you very much for your talk. Very nice ideas and yes, things to think about. I particularly appreciate your use of term computational literacy, instead of computer science education or computer literacy. And about this, I would like to ask you about something about your definition of computational thinking, which at first I liked a lot. But then I thought from the point of view of teachers, how it might sound, because if I remember correct, maybe you can go back to it. It is like ask what you can do with computers, which can be misunderstood as I use an app for doing something. So we have this common confusion between using using computing device and using computation, or using computing, or using programming. So those questions, for me, it's clear what you mean. But for a teacher or for a kid, it might be misleading. What are your thoughts about it?
Yeah, and that's, I do try at the beginning of the learning process to differentiate computational literacy from computer literacy, because most of the time people are expecting computer literacy, like how do I use the computer, how do I use this app, that sort of thing. And that's also why we use I am insistent on using programming, is just because that's the thing that they don't have experience with. And so by showing them that sort of paradigm for solving problems, it helps them to differentiate what's the difference between using something that's created versus creating something that I can use.
One question regarding the balance between application-specific things and general concepts of computer science. How do you see this balance? We in Switzerland have this very dedicated, practical, professional education system. I mean, the wife of your president came here to look at it. How is that seen in the US? These very specific skills that people need in their professional life, in their academic life, versus the more general concept. Do you see, how would you put the balance there?
So I would skew the balance very much towards the disciplinary side when we're talking about integrating computing with other disciplines, just because it's hard enough to get into these other disciplines. I'm basically, shoving computer science into places that other people don't think it belongs. I think it belongs, but I don't want to make that computer science or computational aspect intimidating in any sort of way. And like I mentioned, in the second year that we work with people, they're much more open to exploring more advanced concepts. So when we're first working together, it's very much, let me teach you, or let me help you teach in your discipline. And then from that point, they're more interested in, I want to try to do this thing, and then I can say, well, then you need this sort of concept or this sort of tool.
Thanks a lot for the presentation. I have a question about implementation fidelity, for lack of a better term. You train them, you teach them how to integrate into their classes. Have you done any follow-up work to see how actually are they maintaining that kind of practice, or maybe also the quality in terms of how they integrate certain ideas? Do they fall back to the edtech version of it, or keep up the computational literacy approach?
Yeah, and so we don't do a lot of follow-up in terms of after they're out of the program. We just work with them in student teaching. But this is part of the benefit of giving them those predefined activities, is that they don't know the edtech version of it. Well, some of them do, because I said some of the ones that I've created are the edtech version of it. And they do pretty well if we give them a predefined activity that they've created a lesson plan for, because they don't really know how to modify the program or any sort of way that they might change the activity. So at least in that first use, which is where we'd worry a lot about fidelity, they're doing pretty well. And I think if they're not continuing with that, it's more like they're just not using the activity at all, rather than changing it in a substantial way.
So I think, again, thanks a lot, Lauren, for the talk.